What specific problem does your paper address regarding the relationship between reasoning length and model performance in large reasoning models, LRMs?
The paper addresses the issue of inverse scaling in large reasoning models, LRMs, where extending reasoning length can lead to a deterioration in model performance rather than the expected improvement. Specifically, it demonstrates that as LRMs are prompted to reason longer, they often amplify flawed heuristics, resulting in decreased accuracy across various tasks. For instance, in simple counting tasks with distractors, models like Claude Opus 4 and DeepSeek R1 show significant performance drops as reasoning length increases, indicating that longer reasoning can distract models from relevant information. Additionally, the study reveals that models may misattribute relationships in regression tasks, shifting focus from genuinely predictive features to spurious ones as reasoning extends. Overall, the findings suggest that naive scaling of test time compute can exacerbate existing flaws in how LRMs approach problem solving, highlighting a critical gap in their alignment and efficiency.
How does the proposed method for studying inverse scaling work? Illustrate the steps and components involved in your experimental setup, particularly the differences between controlled and natural overthinking setups.
The proposed method for studying inverse scaling involves a systematic evaluation of large reasoning models, LRMs, through two distinct experimental setups, controlled overthinking and natural overthinking. In the controlled overthinking setup, reasoning length is manipulated by prompting models with specific keywords, e.g., think harder, and setting defined reasoning budgets, e.g., maximum tokens. This allows for a direct assessment of how performance degrades as models are forced to extend their reasoning. Conversely, the natural overthinking setup permits models to determine their reasoning length without explicit budget instructions, enabling a more organic evaluation of their reasoning processes. Both setups involve measuring performance metrics, such as accuracy, against varying reasoning lengths, but the natural setup aims to eliminate confounding factors introduced by explicit instructions, thereby providing insights into how models naturally handle extended reasoning.
Can you provide a simple yet illustrative example of how the reasoning process degrades performance in your experiments, particularly in the context of misleading math tasks? Walk through the steps of the reasoning trace of one model as it encounters distractors.
In the misleading math tasks, we observed that as Claude Opus 4 generated longer reasoning traces, its performance deteriorated significantly due to distractions from irrelevant information. For instance, when presented with a simple counting question like, "You have an apple and an orange," the model initially recognizes the task's simplicity. However, as it encounters distractors, such as misleading numerical statements or Python code snippets, it becomes increasingly fixated on these irrelevant details. The model starts to incorporate unnecessary calculations or code analysis instead of focusing on the straightforward answer, which is 2. This fixation leads to incorrect conclusions, as the model's reasoning process shifts from a clear understanding of the task to an overcomplicated analysis of the distractors, ultimately resulting in a drop in accuracy from near perfect to around 80% with extended reasoning. This pattern illustrates how extended reasoning can amplify flawed heuristics, causing the model to misinterpret the task's requirements.
What are the theoretical or practical benefits of understanding inverse scaling in test time compute for the development of more efficient and reliable language models?
Understanding inverse scaling in test time compute is crucial for developing more efficient and reliable language models, because it reveals specific failure modes that can arise when models are prompted to reason for extended periods. The paper highlights that longer reasoning can lead to performance degradation, as models may amplify flawed heuristics or become distracted by irrelevant information, which ultimately affects accuracy. By identifying these patterns, researchers can refine training regimes to mitigate the risks associated with overthinking, ensuring that models do not misattribute relationships or rely on misleading signals. Additionally, recognizing the conditions under which inverse scaling occurs can inform the design of evaluation tasks that better capture the complexities of real-world reasoning, leading to improved model alignment and safety. Overall, this understanding can guide the development of models that balance reasoning length with accuracy, enhancing their practical applicability in various contexts.
How did you validate the effectiveness of your method in measuring inverse scaling? Discuss the experimental design, datasets used, and the metrics that demonstrated the performance changes across tasks and models.
To validate the effectiveness of our method in measuring inverse scaling, we designed a comprehensive experimental setup that included both controlled and natural overthinking conditions. We utilized a variety of datasets, including simple counting tasks with distractors, regression tasks like grades regression, and logical reasoning puzzles, such as zebra puzzles, to assess how extended reasoning affected model performance. Performance changes were measured using accuracy metrics, root mean square error, RMSE, for regression tasks, and qualitative analyses of reasoning traces to identify patterns of distraction and misattribution. Our results consistently showed that as reasoning length increased, models like Claude Opus 4 and DeepSeek R1 exhibited significant performance degradation, confirming the presence of inverse scaling. Additionally, we plotted performance metrics against reasoning lengths to visualize the inverse relationships, further substantiating our findings across different tasks and models.
What specific results did you find regarding the performance of different models in the context of extended reasoning? And how do these results highlight the implications of inverse scaling for AI safety and model alignment?
In our study, we found that different models exhibited distinct performance patterns during extended reasoning tasks, particularly highlighting inverse scaling effects. For instance, Claude Opus 4 showed a progressive accuracy decline in both controlled and natural overthinking setups, while DeepSeek R1 experienced severe performance degradation, dropping from 70% to 30% accuracy with increased distractors. In contrast, OpenAI O3 maintained greater stability across reasoning lengths, although it still demonstrated some noise in performance trends. These results indicate that extended reasoning can amplify flawed heuristics, leading to misattribution of features in regression tasks and increased fixation on irrelevant information in counting tasks. The implications for AI safety and model alignment are significant, as prolonged reasoning may exacerbate concerning behaviors, such as self-preservation inclinations, suggesting that naive scaling of test time compute could inadvertently heighten risks associated with model misalignment.